This is the first video recording from my residence at Geetham University campus, and the things are not very ideal. I have set it up somewhat reasonably. Okay, let us see how the thing works. Okay, the lighting may also be a problem. Okay, with all this gripe, let me start. Okay, this is the second session of intuitive ideas of measure theory. In the last session, what we did was we are trying to say how to extend the notion of length or area or volume, generally measure, from the notion of intervals. We know the length of an interval, how to extend to large class of subsets of R. In fact, we want it to be all subsets of R. Then we found out what are the ideal conditions I would like to have. Like it should be translation invariant, it should be magnification, and the new length should be the original length of the interval, and monotonicity, whenever A is contained in B, length of A should be less than or equal to length of B, all these things. Okay, so with this we did. Okay, now how to set such a machinery? So what is the idea we want to do, explore this time? Let us start with the notion of a length of an interval, then how to generate the notion of a length or call it a measure of any arbitrary subset A of R. Okay, what are the ways and means of doing it? In fact, to make the idea clear, I will stick to R2 and Rn because I can draw lots of pictures. Okay, because in R, if I want a subset of R, what do? Okay, finite sets, empty set, all of R, some interval. Okay, very complicated sets we can't draw, try to develop our intuition. Okay, so that's what we are planning to do. Okay, I hope you all enjoy. Let us get started. And I said this is the first time, there will be a lot of hiccup. Okay, you have to bear with me. Let us get started. So as usual, first, this is the YouTube channel of mine. You can see that. And this is the email ID. Whatever concerning about my video lectures, please write to this. Don't write to any other email ID of mine. Okay. You can also download the list of videos from my channel. Okay, from this site. Okay, this site. Okay, or you can also scan it. Then search for a list of videos. Okay, and the idea of that PDF file will contain the list of videos, the description, their URL, and the references if necessary. And also it gives the order in which you can learn a subject if you want to learn new. You can also do search. Okay, if you already know some subject but you want to look at some particular theorem or result or concepts or example, okay, you may be able to do that. Okay, that's the idea. So let us get started. So what do you want? Goal is to extend the notion of length of an interval to length or measure of A, where A is an arbitrary subset of R. Okay, and in such a way that all our requirements are met. What are the requirements? As I said, the measure of an interval should be the length of the interval, and whenever A is a subset of B, measure of A should be less than or equal to measure of B. That is what is called monotonicity. And whenever I scale A by a constant C, the measure should be modulo C times measure of A. And the translation variant, that if I take A and move it by X, then measure of A plus X should be same as measure of A. These are the very basic requirements. And one more important requirement we wanted was, whenever A and B are disjoint, measure of A union B must be equal to measure of A plus measure of B. But more generally, whenever A n increases to A, Okay, then I want measure of A n should increase to measure of A, because that is what is the intuitive idea of exhaustion method of Archimedes. Okay, so I want all these things, finite additivity as well as monotone increasing thing. Whenever A n increases to A, then measure of A n increases to measure of A. Okay, so as I said in the thing, what we will do is we will stick to R k. Okay, k may be any natural number. Okay, and mostly I will take k equal to 2 to draw pictures. Right? Okay. Then I want to define a rectangular interval here. I'll simply call it interval, because I can skip. If you are not comfortable, you can always stick to R1. Okay. Interval in RK. Okay. What is this? This is a form something like some interval J1, interval J2, times JK, JR intervals in R. This is a Cartesian product. Okay. So, for example, this may be my J1 and this may be my J2, then that is going to be this one, and this is included, but these are not there. These are open. Okay. So, won't call it. And I will simply denote length of such an interval J, call this as J. Okay. Length of J by definition is product of length of Ji, I equal to 1 to k. So this is the length, this is the area in k. When k equal to 2, we call it area, and k equal to 3, we call it volume. Okay. So in this case, the area of this or length of this is going to be length of J1. Suppose this is A1 B1 and this is A2 B2, then it is going to be B1 minus A1 times B2 minus A2. That is the length or the area. Okay. Right. Now suppose I am given an arbitrary subset A of Rk. Okay, as I said, assume always k equal to 2 so that you can draw. Okay. Now how to assign the measure? Okay. Let me call it as okay. Let me call measure as m of A. This must be a non-negative number in extended real number system. Infinity is also allowed. How do I do that? Just think of yourself. Okay, this is your living room. Okay, it's a very irregular shaped living room, and you have tiles, fixed tiles. Okay, tiles of various sizes. Okay, this may be very small, but all square, something like rectangular tiles of various sizes. Right? Now you want to pave this with the tiles. These are the tiles of various sizes. Right? So if I want to pave this floor with the tiles, what will I do? I can try to fill it up with various things. For example, I can put a biggest tile here, and tile here, and tile here, and tile here. But there is something, I will put a small tile, I will put a somewhat smaller tile, and there is a space, I will put some tile, and there, like that. Try to keep it. So I may not be able to do, sometimes I may not even fix like this. Right? So the basic idea, therefore, is to cover A with a family. Okay. So you find various tiles, well, let me call it J alpha. Okay, where alpha is in some indexing set I. Okay, where J alphas are all intervals in Rk. Right? Then what do I want? My A should be contained in union Jk. Think of this as tiles, so various tiles, and cover them. Right? Now you have to pay for the tiles. So what will you do? You will try to find out, okay, the minimum number of tiles required to cover it. Okay, so if you try to keep big one here, you will be this will be wasted. So what you will like to do? You will put some smaller tiles and try to minimize the wastage. Do you follow that? Please follow the intuition. Okay, just don't listen to my thing. Okay, so the basic idea, therefore, okay, now how much will be the cost if I do that? Yeah, okay, think of this measure. Okay, length of J as the cost, then this will be how much cost I will be doing. J alpha is over I. Okay. Now this is infinite. This phi is infinite. Okay. It could be finite or it could be infinite. In case if it's infinite, it's countable or uncountable. Let's not worry about such things now. Okay. So I have to somehow find this. Then I try to minimize this. Okay. Please try to follow. Spend time. If you have a friend, discuss what we have done so far with. Pause. Review. Proceed. Okay. Let me go back. So just to follow the intuition, think of A as a area and you want to follow tile rate. Tiles of various size are available. Then what you try to do, you want to pay for tiles, so you try to minimize. Okay, maybe square feet. Okay, the tile cost depends on square feet. Then you try to minimize, pay a bit, and again it may overshoot. Then try to put a smaller tile so that you can fill it in and try to minimize. Okay, number of square feet of tiles which you pay. That's what you do. This is the basic idea. You understand? Right. Now the question now, in real life, I would like to use only finitely many tiles. Okay. Right. So, because I am not going to put small tiles of various sizes, it may not be possible also. But in mathematics, we have to do it. Okay. So the next question arises, why can't I live only with finite tiles? Finite number of tiles. That is, I look for A. Okay, I look for a family of intervals j alpha running over the indexing set I, but I is only finite. So that A is contained in union of j alpha varies over I, where I is finite, only finite many tiles. Right, this must be the natural thing. Right, so why can't I? Okay, that will be easy. So that I don't worry about infinite sum, etc. Right, but there is a problem. What is the problem? I will say that okay. What is the problem? The problem is, see, I run out of this thing, so I am finding it difficult, right? The problem is this. So can I restrict I to be finite? That is, A, so let us say, is contained in I equal to 1 to n. Ji's are intervals. Okay. Now there is a problem here. The problem is the following. Suppose I take the interval j, my A to be let's look at the interval 0 1 closed interval. Okay, let my A to be the rationals intersected 0 1, right, and B naturally is a complement. Right, now you see A and B are disjoint and A union B is 0 1. Right, now we can prove. I am not going to stop to prove this. Okay, can be proved. We will see it later sometime. Can be shown if Ji 1 less than equal to I less than equal to n is a finite cover. Let me call it the word finite. It's a cover, finite cover of A, where these are all intervals. Then okay, the summation length of Ji, okay, then 0 1 is contained in union Ji I equal to 1 to n. Remember, what do I mean? A is contained in union Ji I equal to 1 to n. If you say that it is a finite cover with this property, then I want to say entire interval 0 1 is contained in this. Hence, okay, the length of Ji is always greater than equal to 1. Therefore, if I take my measure of A to be in some sense minimum of all such possible covers, okay, that minimum already is greater than or equal to 1. Similarly, you can show minimum of this B is also greater than or equal to 1. Right? But remember our one of our requirements must be measure of A union B. If A and B are disjoint, I want it to be measure of A plus measure of B. So this fellow is greater than or equal to 2, but remember this is nothing other than measure of the interval 0, 1, because A union B is 0, 1, but another requirement is this should be length of 0, 1, but that is equal to 1. So I want 1 is greater than or equal to 2. I get 1 is greater than or equal to 2. This is absurd. So please try to understand what we did. So given a set A, I wanted to cover it by means of intervals. Okay, if I want to restrict myself to finite family of intervals, okay, then if the set A turns out to be rationals in the interval 0, 1, okay, if this finite covers the rationals in 0, 1, it actually covers the interval 0, 1. Okay, and hence the so-called minimum, whatever it is, infimum, if you want, should at least be 1, greater than or equal to 1. For similar reason, the same logic applies to the irrational 0, 1. So what do I get? So I have m of A plus m of B is greater than or equal to 2, but that is equal to, by our requirement, finite additivity, it should be m of union B, but that is m of the interval 0, 1. But another requirement says it is the length of the interval 1. Therefore, 1 is greater than or equal to, that's a contradiction. Don't you think it's very interesting? So this shows we have to allow infinite cover. That is, if I want to say my A is contained in union of Ji, I varying over capital I, the indexing set, I should allow I to be an infinite set, possibly. I can also start with finite because any set is allowed. I don't want to insist it's always infinite. Okay, I should allow infinite collection. Is that clear to you? Okay. The next question. Can I allow this I to be uncountable? Because you know, you are all MSc students now. So you know that infinity has two things, important things, countable and uncountable. So okay, can I allow uncountable collection? Just think again. Let's look at closed interval 0, 1. You see uncountable enough. Singleton set x is in 0, 1. Right? Do you see some problem there? Because therefore, if my Ji equal to singleton x, okay, so this is a disjoint union, right? So I may want it to be, okay. Now, in some sense, here my closed interval 0, 1, let me go back. Many of you may have problem with what I am showing. I thought I wanted always plain. So I want, let us say A equal to 0, 1, then I can write my Jx to be singleton x. Now you may understand why this is an interval. Okay, for me, given any pair of numbers in R, the interval AB makes sense. This is set of all x in real numbers. X is greater than A and x is less than B. Similarly, let the closed interval, open interval, semi-closed. All these things, okay, you can define similar conditions. There are two conditions. Now notice that if my A is 2, B is 1, my x must be greater than 2 and less than 1, that will be empty set. Okay, I am not assuming A must be less than or equal to B. You understand? Okay. Now suppose if I take A equal to B, then what does it mean? What is the closed interval A, B? That is set of all x in R, so that x must be greater than or equal to A and x must be less than or equal to B, which is A. Therefore, x equal to singleton A. You understand? Therefore, these are all intervals for me. Okay. Therefore, A is a uncountable union of singleton sets. Okay. Now, what is the length of this? Notice that this Jx is contained in x minus 1 by n to x plus 1 by n. This interval. And by our requirement, the length of this interval is, okay, this is contained in, sorry, call it Jn, okay, Jxn if you want. Okay, length of Jxn is 2 by n. If you want measure of this also should be the same. Right? And by monotonicity, therefore length of Jx should be less than or equal to length of Jxn, which is 1 less than or equal to 2 by n, therefore this must be 0. Right? Therefore, I may get length of A to be, I may get length of measure of A to be in some sense measure of singleton x as x varies over A. Okay, but this is going to some sense 0 for all x in A. Okay, but remember this is an uncountable sum. So we do not know what is the meaning of this. So pause, review, proceed. So you will see something very interesting. Please bear with me, go through it. Do not want immediately to go into measure theory. Okay, this kind of thinking will make you understand analysis better, and also you will enjoy when we learn measure theory. Okay, now what do I do? That means, let us say, look, take stock of the situation. What do I have now? I have an indexing set I which is uncountable. For each I, let me say that I have a real number ai, non-negative. Then I want to give a meaning to summation ai, I in capital I. Right? If I is countable, then I can write ai as a1, a2, an. Then I can write an ordinary infinite series. Then I know the definition. Do you understand that? But that's not the situation I have here. So how do I surmount this problem? Okay. Learn these things, because these things are again going to be indirectly useful to learn measure theory later. Okay, please bear with me. These are the things which are never done. Okay, people just immediately want to define through theorems. Okay, a lot of thought has gone into this. I want to explain how things, at least the way I thought. Okay, let us go back. Okay, so suppose I is an indexing set, any indexing set, and AIs are non-negative numbers for each I in I, then assign a meaning. In such a way that if I is countable, we get back our usual definition. If I is finite, then I should get a1, a2, an. Let us say I equal to 1 to n. Yeah, then I should get this must be equal to a1 to an. If my I equal to, let us say n, let us assume countable, but countable infinite. So after a bijection, let us assume it's n. Then the meaning of this should be equal to the meaning of this. This is I in I, this is n in n. You understand that? Yeah. Okay. So this is a very, if you have done in my real analysis course somewhere, you must have seen this. You know, in the real analysis book, I think I have done that. So the trick is, okay, go back to summation an, okay, n equal to 1 to infinity, okay, let us assume an are greater than or equal to 0, right? So what is the definition? We say this is conversion, the sum equal to s if I look at Sn, which is 1 to k, 1 to n of a k, this converges to s, okay, and these are all non-negative, Sns are increasing, right, and therefore I know this is conversion if only if Sns are bounded above. All these things are known to us, right? Now I want to get this s in a slightly different language, in a different method. Okay, how do I do that? Let us look at. For any finite subset f of n, okay, let me put sf equal to summation I in f. Notice that this is actually unordered. Why? Because my f is, let's say, 10, 7, 100, 21. Okay, what I am writing is a10 plus a7 plus a100 plus a21. Okay, in whichever way, there is nothing like that. You understand that? But due to associativity, commutativity, this makes sense. This makes sense. I am teaching all these things because I hope you are all MSc students. You should slowly learn to deal with this kind of thing. Okay, teachers don't want to give you to think deeper. They want to make life easy for themselves or for you. Is that clear? Okay. Now suppose my f equal to 1 to n. Okay, then what is sf? Sf could also be an plus an minus 1 plus a1, but it is same as a1 plus an, which is same as sn. Do you understand this? When f equal to 1 to n, my sf is the same. So what I want to claim is, let sigma equal to LUB or supremum of SF, where f is finite. That is, for every finite subset S of f of n, formulate the finite sum SF and look at the LUB or supremum of all these things. Okay, we claim that sigma is S. What is S? S is the LUB of Sn as n varies over n, and sigma is the LUB of SF as f is finite. Okay. First, notice that, as I already said, each Sn occurs in SF. Why? Because I take f equal to 1 to n, then SF is nothing other than Sn. That's all we saw. You understand that? Therefore, this collection Sn as n varies over natural numbers is contained in SF and f contained in I finite. Sorry, n and n finite. Okay, my handwriting is bad. I still have to get used to that, as I said. Okay, then again recall, if A be a subset of B is R, and then LUB of A is less than or equal to LUB of B. Therefore, S is less than or equal to sigma. Okay, pause, review, proceed. So, on the other hand, if f in n is finite and let n equal to maximum of k, where k is an f. Okay, this exists. This is a natural number, right? Now notice that SF is less than or equal to Sn, because Sn will be a1 plus a2 plus an but we know that my subset F is contained in 1 to n, right? Therefore, S F, which is S of this set, call it finite set Fn, okay, Fn, okay, is less than or equal to this, okay. Therefore, what I have shown, for every F, which is subset of n, F finite, okay, Sf is less than or equal to Sn for any n, which is greater than or equal to maximum of k is in F, right? Therefore, so again let us look at, so I have a subset A or B. What I have is, for each A there exists a B such that A is less than or equal to B. Then I claim LUB of A is less than or equal to LUB of B. Call this alpha, call this beta, we will prove that. Now let us look at any A, right? There exists a B such that A is less than or equal to B, but that B is less than or equal to beta. Therefore, this shows beta is an upper bound of A, but alpha is the least upper bound. Therefore, alpha is less than or equal to beta, right? Therefore, what I have shown is, okay, this set is F in n finite. This is a subset of Sn, n over n, sorry, Sn, n, this is a subset of this, right? But what I said is, this is my A, this is my B. For every element Sf here, I can find Sn, so that Sf is less than or equal to Sn. That's all we proved, okay? Therefore, LUB of this A is less than or equal to LUB of B, but this is sigma, this is S. Therefore, sigma is less than or equal to S. Hence, we conclude sigma equal to, therefore, S and sigma are the same. Pause, review, proceed. Oh, I didn't even start, so I have no idea when I started. Okay, so let us try to understand what have we shown. Here I have an infinite series of non-negative terms. We have the usual definition of convergence and the sum of the infinite series. Okay, what did we do? Look at the partial sums Sn, and if Sn converges, its increase is equals, either it converges to a real number, or if it's not bounded up, we will call it as infinity, right? Therefore, the sum of a series of non-negative terms n, okay, is defined by using partial sums. What we did is slightly interpreted in a different way, right? It is same as supremum of Sf, where F is a finite subset of natural numbers, and what is Sf? It is summation ak k in F. Okay, now you see that this is a very large thing, but in spite of that, we are able to get the same thing. Please understand, this is beautiful mathematics, and we will again see it later in measure theory. Okay, and right. Okay, so let's go back to our case. So now let's go back. Summation ai, I in I. Okay, where a is a non-negative, I could be anything. So I will define the sum to be the least upper bound, okay, of Sf, where F is a finite subset of I. What is Sf? Sf is by definition sigma ai, I in I. Does this make sense? This makes sense. Okay, this is our definition now. Okay. So what have we done? So we are done. If I have an infinite collection of non-negative numbers, okay, I have assigned a meaning to the sum. It could also be infinite. If this is not bounded above, I will call it plus infinity. Okay. So I have assigned a meaning. Now let's go back to what I did. So I have the interval 0, 1, and I wrote it as summation singleton x as x varies over a, where a is this, and we know therefore the sum will be m of singleton x, but we saw these are all 0, right, as x varies over a, therefore the sum is going to be 0, right. So I would expect the length of this must be 1, but it is equal to this, therefore the length should be equal to this disjoint thing. But remember, now you can also see why we need countable additivity, because now I am assuming, are you following the subtle point? My 0, 1 is not a countable union of disjoint sets, it is an uncountable union of disjoint sets. Okay, you understood? So this is again not acceptable, therefore we restrict ourselves to countable collection. Let me try to write a little more legibly, even I can't read. Collection Jn okay, Jn of intervals, so that A is contained in Jn. We will call it countable cover. Okay, so let's go back. So I have a subset A of Rk. Now what do I look for? I look for a Jn, n, okay. I write it n because it could also be finite. I don't write any in n because it could also be finite collection. Okay, it's a countable collection. So if it may be 1 to n also, or 1 to infinity. Okay, countable collection of intervals. What kind of intervals? It could be any kind of intervals, any kind of finite interval. That is, it may be product of intervals of this kind. I don't care, because all of them have the same length, so I don't want to worry about. So I want A to be contained in union Jn. Okay. Then I define, okay, this collection, let us call this as J, okay. I define, this is a notation, so I want to define M of A, the measure, to be the GLB, or the infimum of this collection. M of length of Jn, okay, n, where A is contained in union Jn. Please understand what you have achieved. Okay. So what we say decided is, now we will try to do countable paving by means of countable number of tiles. Instead of finite number of tiles, we allow possibly infinite, but only countable. Is that clear? Right? Then what do? So I have various possible ways of paving this by means of tiles, but I try to choose the minimum one. Minimum meaning intuitively minimum. So in analysis I call it infimum. Okay. So the total number of areas you want to cover. Okay. So we'll go back and try to see what we have done. So I have this. What I do is I'll cover it by means of small tiles, and so what I have is an approximate area. If I look at all these tiles, so please, I don't have patience to draw it completely. Okay, allow me to do faster. Okay. like that. Okay, some holes you are covered, right? So the area that is the measure of this, you can see is less than equal to measure of all these things, right? Okay, measure of j, where j's are these things. Okay, if you want write n, but this is equal to length of jn. Okay, so what do I want to do if I want to approximate? It's a better if I want to get a better approximation, I have to take all possible pavings, all possible collection, and take the minimum. This is all the idea. Okay, so it seems to be from this you can see, so for each a subset of rk, I have measure of a. It could be an element in 0 to infinity, right? What are the obvious things? In fact, it doesn't take much time to say is that, okay, measure of an interval is the length of the interval. Little subtle argument, but it can be proved, but not difficult, at least in the case of R. Okay, equal to 1. Okay, second thing is monotonicity. If A is contained in B, okay, measure of A must be less than or equal to measure of B. And third, okay, measure of A plus X, that is, it's a translation invariant. Okay, we can also prove the following. Okay, measure of union AN is less than or equal to measure of union AN. This is what is known as countable subadditivity. But measure of A union B or measure of union AN equal to summation measure of AN if ANs are pairwise disjoint. This is false. Okay, with this construction we have a problem. So in the next lecture, what I will try to do is I will try to see our definition of M, call it measure. Okay, we have defined for all subsets A of Rk, right? Okay, this satisfies almost all the desirable properties. What are they? First is measure of an interval is its length, and it is a translation invariant. It is also monotonicity. It is almost countable subadditive, and it works with respect to scaling. That I forgot to write. That is, okay, let me write that. It also is true, the fifth property, make it as fourth property, M of Ca equal to mod C to the power k into measure of A. This is also okay. So all these things are very true, right? This is 1, see I already wrote wrong, 1, 2, 3, 4. These things are all correct. The fifth one is countable additivity. There we get only countable subadditivity. That is also easy to prove. After this is proof, we can prove. This is also proved. But when you want, we will see why we can't have that. So in the next lecture, I will try to construct a sequence AN of pairwise disjoint sets in R, and we will see why it cannot have countable subadditivity. Then what do I do? That is the point of the next lecture. Okay, and I know these are all vague because people never expect ideas. Line by line checking proof is very always easy. Okay, but when you want to generate ideas and feel the intuition, it's always difficult. So please, okay, go through it, discuss with your friend. Don't worry, don't try to make an attempt to understand 100%. There is no rigor. We are simply playing with ideas. Okay, I hope you liked it. We'll meet again. Stay tuned.